Oh, okay. So, hello everyone. Do you have questions before we start with the other topic? Anything related to, oh my goodness. Anything related to whatever was discussed in the previous set of the module? Nothing at all? Goodness gracious. No. Does this work? Does this work? So if not, nevertheless, we're going to discuss how there's actually somehow misleading, but the thing that I'm trying to say is actually this is the lesson regarding reinforcement learning, nevertheless. And that is done to see explicitly how we could correlate skills with strategy. Because in the other one was somehow implicit, given though the strategy itself was always deterministic and we were always assuming the agent to be rational. In here, by adding probability, we're also leveraging a bit more of variety too as an outcome. So let me click on that. Does that go? Yes. So in here, we're going to see marginally, but only to a minor extent, how we could have like positive feedback in games as a premise of reinforcement learning. Because that is actually what the algorithm is going to leverage in order to learn. And that is actually why we're going also to consider that as a way to provide feedback in the video game. Still, we are going to model only one agent out of simplicity, because discussing in the meanders of multi-agent reinforcement learning is going to be too much for just 1 hour, so I'm just going to focus on one simplistic model. And then we're trying to characterize that in terms of positive and negative feedback as per the first line. And would say that we would also tune our algorithm to be more or less expert through a farsightedness parameter, which is always referred to gamma in the literature, even if you're using like RL agents or ML agents in Unity. And then still we want to discuss a bit which are the limits of this model. And then rather than discussing the pseudocode, I might discuss straightforwardly the C# code directly, but either way it should be fine. So we're only going to tackle part 1 due to time constraints, okay? And the next time we're just going to do the second last topic of the module. And just to as a matter of a recap, the last lesson will be recapping some of the topics of the module, plus answering potential questions regarding the coursework, and doing like frontal lessons on what the resit exam might be about. So we're going to see a bit of the stuff, so you are prepared just in case you need to take the resit. The thing that we're going to discuss here is actually just one agent for the sake of simplicity and for time. And those are often referred into literature as one-person games or games against nature. Why are we doing that? Because that still could be generalized to multiple agents, but is actually more easy to discuss if we're just having one agent. And then, before doing that, we should ask ourselves whether we are able to model an agent which is capable of taking meaningful decisions. And even in there, we're just limiting the decisions to a set of actions that are viable, not the set of all the possible actions in total, which is often the same limitation going on in computer science, which is also compliant with video games. We might assume that no decision is with no effect, otherwise doing one action rather than the other is completely irrelevant. So there should be like a differentiation between the two, if possible. But among those, we need to find one optimizing the goal. So beforehand, the goal was optimizing like the value, which was like the total amount of resources in the world. In here, we want to maximize the reward, but somehow they are similar into the idea. And so in here, we might freely assume that we don't have an opponent, but we have a world summarizing within it actually what is your opponent. So that's why those are called like game against the world. But you could say that your world is basically your opponent or your set of opponents. And still, that is actually why those are relevant. And to some extent, those are also applied into robotics and to planning theory. And then it depends on what you want to do. But still, if you have multiple choices and you want to train an algorithm, that is one of the choices alongside with planning. Why are we discussing that? Because it's a very well-studied part in literature, how an agent perceives the environment, and depending on that, how are they making decisions. And that is actually the thing that you are seeing here, basically. So the thing that is happening, and then we're going to contextualize that to reinforcement learning, but there are sensors through which the agent is probing the environment. So in Unity, that might be, for example, a ray casting or something, or receiving a collision from which that is actually the sensor that you're going to have. So you have a critic, which is going to provide some kind of feedback, but somehow that is somehow convoluted. So you might have a simplification of that, which is we are having a mental plan, which is trying to make sense of the environment that I'm sensing. And after conceptualizing that, then I have like an internal memory somehow postulating what I might do with this kind of information. And then depending on that, then I know via the actuators how could I enact my action. And my action might either self-update my internal state, as we're going to see, but definitely might do an action on the environment. And that relates to, so for example, to state machines, that equates to a transition from another state to another. And environment-wise is I'm changing the environment. And thus, in the system, the thing that we want to do is actually to be as sensible to also try to always do like a finite set of actions, but then we want to be flexible to them with respect to the environment that we are perceiving. So that's how that is formalized usually in reinforcement learning. So you always have an environment and an agent, but in here you have that either you're having a reinforcement learning algorithm for which an environment gives you also a reward for the action that you are enacting as a response to an observation. But once this kind of reinforcement algorithm is done, the only thing that is left is actually the policy or the learned model. So either I'm having like a reinforcement learning algorithm, which is constantly updating the policy, or I have like the policy set into stone after training, and that is going to be the only one, not considering the reward anymore, and just taking the observation and providing the action. So that is actually still the rule of thumb. Then you have multiple algorithms in reinforcement learning that are changing what is the policy about, or how I'm doing the training in order to get that policy out. But notwithstanding this, the way is actually the same and reflects a general schema of learning and inference. So there's nothing special. So so some people might say is not supervised, it's semi-supervised. Actually, that boils down to a classification function, because given an observation, I want to say, given this observation, I want to have the action minimizing the loss. So it's just a learning function. That is what you're doing, is just a supervised learning. So how does that relate to video games? Well, even in video games, you might have power and costs. So power in a video game is like a power-up or something, is anything giving a player an advantage. And by collecting that, there are some actions or there are some properties of the system that are giving the player like a positive feedback, okay? That is actually the actual good thing to do, either through animations within the video game or something. And the ultimate goal is, even whenever you are setting up a game, is that the way you are providing positive feedback should be related to actually progressing within the game. Because if you're providing positive loop and there is no correlation with the progression, then you're giving to the player hints that are wrong in terms on how to succeed the game. So for example, let's suppose that you are using any kind of game like, for example, like Civilization or this kind of stuff. And if you're providing like a feedback which is not related to a victory on one of the kinds of victory that you might have in Civilization, then there's actually to no aim at all. So that's why you're having guidances. So that's why you're having like people giving you feedback as non-player characters. So then you might decide which feedback is actually more important depending on the goal that you want to pursue. But still, that's why you're having intermediate feedbacks that are somehow aggregating all the information that you're having in your game. And why it's important to have powers, because you also have costs or things giving the player negative feedback. For example, if you're losing money or if your opponent is doing better than you in a given strategy, or if you're going back to even Civilization as you're trying to have more influence in terms of culture, and city that you conquered actually was conquered by your opponent, for example, then that should give you like a negative feedback because the amount of cities on which you're having influence decreases over time. That might be one. And then the other important part is that there should be always a cost to pay somehow, but that should be like mitigated by the rewards that I might have on the long run. So for example, if I want to be like a if I want to be, for example, a success in the arts, I need to invest a lot of money on university or all this kind of stuff, and then I have an initial costs in order to progress with the scientific part in my civilization. Still, then I have like a benefit later on, but I need to invest somehow at the very beginning, actually a no pain, no gain, basically. And so I need to have some costs, but I need to also know what is going to be my future reward for that. Nevertheless, there might be some kind of shadow costs in as much as a game might not provide the feedback on the disadvantages directly. If that might give, like, for example, a greater chance of losing. And so that is actually just given to the player to plan itself. Otherwise, it will be, like, too straightforward for progressing. And so some of the things might be, like, more nuanced in a game. So basically, the thing that we're doing is trying to use, like, a transition. So those are the thing that we were referring to with a transition model. So what is that about? So usually all the algorithms that we discussed before, and be that like the state machine, hierarchical or simple, or even like the min-max algorithm or the alpha-beta pruning, we're still providing transitions from state to state, because I'm having like a perception of a state. Depending on that, I decide to do an action. The perception in there is more implicit, and still, because everything is submerged within the final score of the system. So rather than having a continuous reward, I have a total final reward, and in here I have like a local reward that should be related anyhow to the global state that I want to reach. So those model always model or map transition to some extent. So the thing is how the positive feedback that I'm collecting is actually helping me to progress in the game. So I'm teaching that now to the perspective of the player, but having that mindset could also help you to better settle up a reinforcement learning algorithm. Why? Because if you're thinking about a strategic game, then capturing an enemy territory leads to the long run to greater resources, because I'm doing that. But, for example, if the collected resources are just resting and are not exploited for advancing your civilization, then the user will never reach the goal test condition, which is, I want to do something in order to fulfill the goal, but if I'm just doing something without applying that in practice, then I'm not actually advancing. I'm just half of a step further, but then I'm not doing my everything to reach the final goal. So that's why it's important that it's not just like the seize the day approach, but it's actually more a chain of actions that you need to consider in order to reach your fulfillment. And that is actually also modeled in reinforcement learning somehow. So it's not only one action that does, but it's a chain of actions for which there should be a correlation between I'm following like the maximum reward and I'm finalizing towards a state which is the thing that I want to reach. So how does the algorithm work? Training by experience, by seeing a lot of circumstances happening, and therefore the algorithm learns somehow how much probable is an action to happen. For example, in this situation we are hard-coding the probability, but if we're having like the set of actions, then that is actually the probability of the sequence of actions happening is the thing that the reinforcement algorithm will learn. But in here we are somehow oversimplifying the approach to some low reaching, and that you could also do directly in Unity without any further ado, because actually setting up ML agents is a nightmare in Unity. So, and that if you are interested in reinforcement learning, then I might suggest you to do a dissertation on the topic rather than trying to do that for the coursework. So that's why I'm providing like an easy reaching code base for that. And thus, if you're having a graph, basically you are setting up the entire strategy, and that should summarize somehow all the possible facets that might happen in the world, and then you want to, and all the possible actions, and which are the intermediate states that the world is reaching somehow. So in this circumstance, the states are more reflecting a combination of the states of the agent and of the world, rather just modeling the agent itself, because I'm trying to model an interaction between the two parts. So which are the fundamental parts from that? So in there, you'd have like the discount rate, which is how much, given the training experience, I could forecast what might happen in the future. So to maximize the total reward and ignore the local reward. So I'm favoring like having a greater reward in the future rather than seizing the day. So that is actually what the gamma parameter is doing. And then ultimately, I'm setting up a plan, which is the likelihood of performing a given action when the player is actually on a specific state, because that is also reflecting what you'd have like in state machines, okay? Depending on the state that I'm in, then I might decide to do a set of actions or the other. And similarly, that is also in reinforcement learning. The only difference is that I also have, I'm using like probability to learn the frequency of an action happening and the likelihood that that action is going to lead me towards a given state. And I'm also trying to infer then which is the best action to perform. So if you're just taking like the state machine, then it's somehow passive in a way that you're taking the input from the outside and directly from that you're deciding. And here is actually more proactive, because given the prior experience on training, then you're deciding which is the best action to pursue, and you're just picking one, or you're giving a grade of likelihood of doing one action against the other. And then you're having also something related to goal-oriented action planning, because the literature in games is actually quite finicky and not very good. So if you're looking blogs online, they are having something called insistence value, which is the likelihood or the how much I would like to reach a specific state, and I have like a value. So, and that is somehow also what you're having in reinforcement learning. So at the end of the training, with this kind of algorithm, you'd have like a V state, for which is actually saying how much I would like to reach that node in order to fulfill my final goal. So at the end, I'm learning the plan, so what action I want to do based upon the insistence value that I'm training. And then, depending on this value, then I'm determining the plan. So that is actually how the algorithm is doing. Basically, you could think about this insistence value as the aggregator of the combined provision of the probability of an action happening and the reward that I'm obtaining from performing the action. So before discussing the model itself and how that is structured, do you have any questions so far? Okay. So that is actually how any kind of reinforcement learning algorithm looks like. Then you'd have deep neural networks or any kind of wizardry that you're having down below. But everything boils down to having actions, having a reward, and the probability of transitioning from state to state. And that's it. So that's what you're having. Then you are just overcomplicating, you're adding superstructures, but that is actually what is happening. So this is actually discussing like, how do I pass an exam kind of thing. So this is actually a student starting on reading day 1. And they have the choice, either I want to study or I want to party. Then depending on that, if I'm studying, then I have like, I'm bothered, I'm not like, I do not like that. I prefer to actually have a party. So the negative reward is actually there, and if I'm happy, I'm providing myself like a positive reward, but then after the party, I might be affected by a headache, giving me even like a worse reward. So, but still, if I'm stuck within a seize of the day approach, you'd see I might just circle in there and always prefer to party. So suppose that we want to study then, with a given probability. Then I'm having the second day. Even in there, I have the choice of either studying again or to party there. And then in there, you'd have, just like for modeling purposes, that I could either have a very strong headache, and so I'm forced, I'm not very relaxed, I need to go back to settle down a bit, and then I need to take more time to study or to recover somehow, or I want to study and actually progress. And that escalates up because, and still you're having the same setup on which the reward is negative. But at the very end, you're having a very higher reward in the circumstance that you're studying and passing the exam. Why? Because you might have like economic contingencies that are forcing you to get a degree earlier on and not repeating the exam and all this kind of stuff. Thus, anyhow, the thing that you want to do is to have reached like the maximum reward at the end. And that is actually what you're having. So what is actually the great difference as compared to simplistic state machines? So as a state machines, you have labels associated to actions, but as I was discussing beforehand, in here you have a probability value, which either model to some extent the strength of a player. So let's suppose that I want to say, for example, you want to model the probability of succeeding in something, then that is actually how you're modeling that in graph terms. So either you're having like a log or history of what is happening from which you're defining the probability, which is not advisable at this stage of the program, or you're just using a graph and hard coding the strength of the player or of the opponent by setting up the probability of that action to be successful, and if successful, you are transiting towards the other state, okay? So you're having a probability summarizing either the strength of the player or actually how likely is this action to happen, for example, from the external world, for example. And that is not only associated to a probability, but also with a reward value related to the environment giving me a reward on what I'm doing, basically. And that is actually the R value, which is not necessarily between 0 and 1. It could also be negative just to provide a negative reward. And in here, I'm supposing that the reward is just perceived as the student perceives the outcome of it. So it's just like an internal setup. But in robotics, you might think about that. I'm perceiving the environment, and then I have a feedback on the action that I'm doing. Thus, I'm also providing like a self-reward function. but I'm just governing myself, or I might provide constraints that are violated, thus those are actually providing like a negative reward. So how then do I set up like the game being well balanced? So because I do not want to have basically an irretrievable advantage until they are at the very end, because if I'm saying, for example, within the game, okay, if you're studying, you are immediately having the reward, that is actually quite simplistic and doesn't help with variety and with a player to build up a strategy, for example. Then that's why I also provided in this formulation of a simplistic video game the reward as such also, because there might be like an initial choice, and having like the best choice should also build up to creating a plan for the player, thus making the game more challenging. Nevertheless, also early mistakes should not make the game unwinnable, because if I decide to go one party one time, it's not the end of the world, and still I might be always able to go back and study when I feel that appropriate to fulfill my goals. And also adding the uncertainty of the reward makes the game more desirable for many players, because then it's actually just subjective, but some players are like do like better a game which is unpredictable rather than something which is quite predictable and they know how to navigate the system, basically. So if by tossing a coin there might be some kind of probability of the actions being slightly different, then I'm building up the challenge for the player, and that makes also that more desirable. So that is actually what I'm trying to fulfill. And also a well-balanced game, in order to increase the sense of progression, should potentially further increase the rewards up until the end. So they are actually saying, okay, you're getting there, okay, you're getting there, this kind of stuff. So that's why basically if you are reaching a high level of civilization, for example, in civilization, then you could also get more actions because, yeah, you unlocked many steps. Thus, you could also do more with the things that you achieved. Otherwise, if you are still frozen on this middle, like on the Stone Ages, then there's nothing more that you can do, and then it's very hard to beat your opponents. So even in there, what is actually happening, then, as I was saying, you are learning something which is still probabilistic because you are having like a probabilistic distribution over the set of actions and states that you're having. And the thing that you want to have is basically at the end of the world, at the end of a game, basically a deterministic policy, if you want, saying at this stage, which is the best thing that I want to do. In this case, you're just taking, after training, the action maximizing the outcome value, which of the training, and in that way you are achieving like a deterministic policy. Otherwise, if you want to have like more of a stochastic game, then you know that you're having like after training a non-player character that has been trained, and I'm not just doing whatever my deterministic policy pi is telling me, but I want to, for example, toss a coin, and depending on the outcome of the toss, then I want to do one of the actions. That could also be done in your implementation, okay? After I train like a reinforcement learning algorithm, I don't want to necessarily abide by the best action as determined by the policy, but I want to perform the action with a given degree of probability, which is directly proportional to the likelihood after training. Then I could also do that. And that should be possible to implement by just using a random number generator within the interval between the minimum value and the maximum value of the training, so to speak. And still, that was also a question that I got, how do I make my agent dumber or smarter? Then that boils down to changing the gamma parameter, okay? So if you're taking gamma equals to 0, then I'm just using a seize the data approach, and then I'm going to be short-sighted somehow. Well, by taking gamma equals to 1, I have the perfect foresight in the future, because I'm always maximizing the total reward, even though the game might be like less challenging. So before doing that, I'm going to show you actually the code, and then if you want, you're going to have the pseudocode in the slides. So before I show you how the algorithm works for Markov decision processes, do you have any kind of questions so far? If not, then let me show you how that works. So, if I have time, I'm also going to discuss this other file, which is variation on min-max realistic with RL. Why? Because with that, I'm also showcasing that once you set up and you know how to determine basically min-max algorithm, you could exploit the same demo that I showed you last week to also use the reinforcement learning algorithm straightforwardly. So you have that file, which is actually showing you how to interact with a model in the same way that you're interacting with a min-max. Thus saying is actually not reinventing the wheel and rewriting the entire system all the time. But most importantly, let's discuss the algorithm first. So that is actually referred to as a policy iteration, and that is actually what is that about. So I have an initial initialization phase on which I'm just using like a random number generator because I'm having like I want to randomly initialize the value of the insistence values initially. And then that's why I'm having like a dictionary associating each node of the graph with insistence value, and that is actually your V. And then I'm just, for example, if I'm having like, then it actually might be quite daunting, but you'd have like a set of mathematical background that you lost after the refactoring of the module, but let me give you somehow straightforwardly. So it goes down to having like using probability. So whatever is the accepting state, that should have like a desirability value of 0, because that is the value that you want end up towards. Otherwise, if that is not an accepting state within your model, then you want to initialize that value to whatever real number. So notwithstanding this, if you want to grasp more about like a number of maximum turns for after which winning the game, you have all the slides, which are just additional material now in the module. So that provides like the sound probabilistical motivation. Otherwise, I'm going not to ask that into any kind of exam, so you just might take that for granted. Okay. And then the thing that I'm doing is setting up the policy, the probabilistical one, and the deterministic policy, on which I have like the node label, so the current state of the game, the age label that reflects the action, and the likelihood associated with that, which is like a value not necessarily between 0 and 1. And then, how does the algorithm work? Is actually working in a loop. As such, afterwards is just initialization. So I'm having a delta value, and that is just being used for determining whether there was any kind of appreciable variation from the previous stage of learning. Then the thing that the algorithm does is for each refinement of the algorithm, so for each refinement of a policy, that is the thing that we're trying to achieve, I'm iterating over all the vertices, and the thing that I'm doing is just getting all the actions that could be done over this node, and for each of the actions that are associated to the node, then I'm trying to get basically the cost, which in here is just the weight, from transiting from the given node towards the target node by providing the specific action. So get cost is basically considering like the probability value, where is actually it? Yeah, so the get cost function, I don't have the ID in this PC, but is basically considering like the weighted sum of all the insistence values that you're having, and in the next step that you're reaching, and is weighting that up by the probability value. But that is also mitigated through gamma. So the thing that you're doing is basically considering, let's go back with the slide just to be clear, but you're not seeing the slides now. What if I'm doing this? Yeah. So the thing that you're seeing here is that you are getting all the outgoing states from the given state that you're considering, and then basically the thing that you're doing with the get cost is considering the insistence value from the outreaching state. You are multiplying that with gamma because I want to consider that more if gamma is equal to 1. I want to completely ignore the insistence value of the state that I'm reaching if that is actually equal to 0. Otherwise, nevertheless, that edge comes with reward, and that is still weighted by the probability of performing the action. So that is what the get, goodness gracious. So that is actually what get cost is doing here. It's taking into account the reward of the edge and the probability of this action to be performed, also the desirability of a value, which is the reaching one, okay? And the thing that it's actually doing is getting how much the new forecast of the desirability of a current node actually differs from the one that I previously computed. So that's why I'm doing this kind of delta computation. And the thing that I'm doing is keeping track of this delta, and then whenever this delta is equal or is beyond like a change threshold, then the algorithm will stop. That might also similar to setting up a maximum number of steps for training, after which I'm stopping, but either way, you're having a stopping condition. That is how all the learning algorithm works. And then in there, how do I determine basically the best policy, like in a deterministic way? The thing that basically I'm doing is getting for all the vertices that are there, and then I'm considering all the action names, and then I'm basically just computing the function that you had before to determine the desirability of the current state given the desirability of the overstate, the gamma parameter, and the probability of performing each action, given that I'm determining the probabilistic policy. And after doing that, definitely I'm also keeping track of, among all these actions, which is the one maximizing the overall reward. And then if I'm also keeping track of that, then I could also set up a deterministic policy saying, okay, at this stage, I want to ignore what is going to be like the all decrease of actions that I could take. I want only to know, given this node, I want to perform this action full stop. So if you're just interested in the deterministic policy, what the code base is doing is basically returning you that. And then it's completely up to you if you want to use reinforcement learning in your code base. Either you're having an agent just taking whatever was the outcome of training for a given state, or the thing that you might do is to have like a random generator deciding on what you need to do. Then I think that we also have another bunch of slides related to the algorithm itself. So I will give you as a self-study how to, if you're interested in this, how to use this policy after training, but just to give you guidance on a general term on how that is happening. Basically, the thing that you're doing here is generating a graph dynamically, given the same assumptions from the previous game. So even in there, you have like a runtime expansion function, basically determining have this state of a game, then what is actually the probability of doing this, which is actually the reward of doing that. So have basically a recursive function building up the graph for you in the same way. So it's actually a one-to-one parallel. And that you could tweak in the similar way. So you have one function which is just set graph recursively, which is building up the Markov decision process given the game that I want to solve, basically. And then the thing that you're having at the end is after generating the graph, in here, if you want, I'm generating a dot file. So if you're using graph viz, you could visualize that graph. And then with a loop is actually the one training the game. So you have like, at the end of the loop function, you'd have like the policy iteration outcome. And then in there, I'm just using the game as it was before. And rather than using the min-max tree or the alpha-beta pruning, the thing that I'm doing is actually using the policy for interacting myself as the non-player character in order to play with a player, which in here is just doing like a random set of choices. So the code base is somehow like a refinement of whatever we discussed last time. So there is actually not a big deal. And so if you want to understand better, okay, let's suppose that you already did in your code base like min-max or alpha-beta pruning, and then I want to say, okay, I want to do the same stuff but with reinforcement learning. And thus I want to have like two agents, one working with min-max and the other, or alpha-beta, and the other one using reinforcement learning. Then the idea is you're setting up the game in the same way and you're having two agents. So that's why I gave you this kind of code base, because if you are engaging with this code, then you are hitting two birds with one stone, basically. You are just need to define one game once, and then you unlock all the mods, for example, for doing this stuff, because there are a lot of overlaps between these topics. Okay, so this is actually my suggestion. So if you want to engage with that, then the code base is there, and notwithstanding that, so basically that is just the mathematical contraption showing you what the code base is doing. But I explained to you via code base most of the time. Okay. Is that working? No, because I haven't clicked it. Here. Going backwards. Good grief. Do you have a backup plan? I suppose so. Okay. Let's have a backup plan then. Okay, so now I'm just showing you the effect of using the algorithm by just changing the gamma parameter. So that is actually showing you what is actually the difference between a novice or, so let's suppose that you want, that was actually the question that I was asked. So you want just to hit, even in this scenario, two birds with one stone. And the thing that you want to do is having, with no effort, two non-player characters, one being dumber than the other. So what is actually the best strategy? Usually you're taking one gamma value to be very low and the other gamma value to be very high. And then you'd have automatically different policies out of that. So what will happen in here? In blue, I'm just highlighting the deterministic policy, which is the outcome of that, but even the non-deterministic policy will be different, okay? So the thing that is happening is that if you're using gamma equals to 0 in that algorithm, then you're pursuing a seize-the-day approach. So you're always preferring like a reward of 1, and you're ignoring basically that you'd have a very stronger reward at the end. Why? Because this value v is equal to 0. The gamma parameter will be always 0, so whatever the contribution of the probability and the reward is always voided. And thus, the only contribution that you're having from v is just like the immediate stuff. So in here, yes, this 9 is actually just a weight between this one and this other 10. But in here, this value of 0.3 is just equating, you see, to the probability of 0.3 and the reward of 1. So I'm just having that the insistence value is reflecting like the immediate reward that I'm having locally. So that is actually what is happening with gamma equals 1. So it will converge immediately because I don't have to do multiple iterations, and each iteration will potentially push the rewards from the final state that I'm longing for towards the initial states. So that is what the effect of this iteration is doing. It's just pushing the reward to the very beginning. So I'm trying to connect the dots. So that is actually what it's doing. And that is not happening with gamma equals to 0 because it's blocking everything and it's just considering the local reward. So at that stage, you'd have that no matter how you are progressing, you'd always prefer to party in the circumstance, given that parting here has always a reward of 1 and starting as a reward of -2, while just starting before the exam as a greater reward because I know that I shall not party at this stage, for example, but still both have rewards, so I'm just privileging studying because I want to have like a higher amount of costs if I'm not getting my degree, basically. The weight associated to each state reflects then the maximization just being local. And if I'm just taking, as I was mentioning before, the maximum reward locally, then you just have like a loop, for example, at the very beginning, parting headache, and never progressing within the game. So that boils down to a seize the day approach, okay? On the other hand, if I'm using gamma equals to 1, then I'm having is like having to some extent a min-max algorithm with probability, so the last one that we discussed the last time, basically. So even in here, then the thing that would happen is no matter how I might have a reward, given that I might fulfill a greater reward at the end of +10, then you'd see that all the intermediate nodes will be more and more desirable. And also the other thing that would happen is that you see in here, I'm also having insistence values that I'm reflecting. I shall never go towards that route. And if possible, I should always go up back to a possibility state where I want to go back to study. And that is also giving you like a mathematical idea how by continuing to study should provide to some extent always a greater reward to the agent, because by doing that, the thing that you'd achieve is basically providing even better feedback. So initially, it's completely up to you, but then I'm studying, then that should be reinforced as much as possible. So if the insistence value goes up, then I'm studying again, the insistence value goes up again, and then after that, I'm studying, I'm passing. So why I'm also saying that, because it's actually somehow relevant to also have in mind, which is the ultimate goal. Most of the people and also most of the students, when they're approaching reinforcement learning, they're also thinking about the seize the day approach. So I want just to provide a reward function, just telling immediately what the agent needs to do, and is never thinking about what the agent wants to provide at the very end. So you might get stuck in a loop, basically not reaching the final state. So not because you're providing a high reward, and that somehow is coarsely correlated to the goal that you want to obtain, then that does not necessarily reflect on the agent going to the final state that you're looking for. So that's why then you need to also set up the reward function so you are guaranteeing that the local reward that you're providing is actually compliant to the final goal that you want to reach. And that is actually the common misconception of people starting to work on reinforcement learning. But in here, I might have like a person which is just studying and not parting any over time, and is just thinking about recovering back. So that is also referred to into games like the dominant strategy. So how do I know for sure that I want to win the game? I want to ensure that my non-player character has always the dominant strategy. By setting the gamma value to equal 1, then I'm always ensuring that to some extent my game is somehow unbeatable, and so it will be very unlikely for the player to be challenged. So that's why usually, and then I will stop here, that's why basically the thing that you need to think about is that if you want to have something more tailored, you might consider either not considering the deterministic strategy, but using like the non-deterministic one and using like a random number generator to pick one of the actions if possible. Thus you're adding a bit of randomicity. Or If you're still thinking that you want to do like the easiest approach, so rather than using something deterministic, you want something deterministic because you don't want to engage with random number generator and picking one from the non-deterministic policy, then my suggestion would be to take a gamma value which is in between 0 and 1. So you're having like a strong agent, but not so strong that is going to always beat your opponent. And that is actually going to be my suggestion. Then the part 2 is actually something more obnoxious, so to say, is just to say that both to introduce why you might use like deep reinforcement learning algorithms, in as much as it might be quite unbearable to define the possible number of states because they might explode, and still also to say why even in logic we're having the same kind of problem, but using deep reinforcement learning is actually not something that we can do for the mathematical background which is required, and we just have one lesson before the recap one in the last day. So I'm just going to discuss something more bare to basics and using logic with that. But still the idea is by even doing very minimal changes to your world and to the inference of what an agent needs to do in a world, even though it's actually very small, then you'd have like an explosion of a number of states. So you might go to 11 million states. And if you are making even a slightly realistic assumption, while if you're taking something to the bare essential, you see it's just 1 million set of states. But still, you're having like a huge amount of problems. So that's why most of the time, neither Deep Blue analyze the entire set of states. So that's why you're having like alpha beta pruning. That's why we're not creating the decision tree, so to speak, all the time, because it takes time and is actually to no avail. So they're just building that on the run. Similarly, even when you're talking about planning, that's why even the GOP that you're seeing in blogs and video games is wrong, because they are modeling the graph, and that is actually not compliant to the current literature. Even though you're having 4 states, still is actually not enough for modeling realistic problems. For example, even like a trapping game might require not having that set up, because in there you're just modeling which are the actions that you want to do and which is actually the likelihood. So actually solving the game rather than doing something low-hanging and easy reachable, actually doing stuff is more complicated and requires to hard code way more states that you would have like in blogs for video games. So that's why next time we're going to see another way just for solvability of games that might be also related to the recit exam. Okay. So that's why for solvability of games is actually better rather than considering all the possible combinations of the actions that you want to perform, having an explosion of states to reduce that explosion as possible. Actually, the thing that you're doing with these other kind of strategies is building the graph on the run rather than hard coding the graph. So actually, knowing how to use graphs is okay, but it's even better to know how to not use the graphs whenever possible and to do without them as much of the time. So that's why the last lesson is going to be how do I check whether the game is solvable. And therefore, before wrapping up, we're going to see another way to do like pathfinding, but over a strategy rather than doing pathfinding over scene to navigate. And before that, do you have any question regarding this, regarding coursework, or regarding anything else? Then if not, just class dismissed, and thank you. Hello. So I'd suggest to go to my office, basically, because I think that there's going to be another lesson within 5 minutes. So I do not want to overbear. And actually, my office should have also this place where to sit basically, and so I'm guiding you where my office is basically. Do you have another question in the meantime? Yes. Sure.
For the coursework, I'm using like a first-person controller package from Unity. Is it okay to build on top of that?
Yes. So basically, that should be fine. You just have to reference how you extended that. So it could be something as minor as a comment, for example, as far as I'm concerned. Yeah. No worries.
Just to double check something.
Yeah, sure.